Hello, you absolute legends. My name is Eric J. Choi, and I'll be going over explainer video 8.1 that goes over the first problem that the professor made up because the textbook sucks. And alright, jumping right into the problem. So before I begin this at all, I just want to explain really quick that there isn't really a reference that we can look back on for this except for the lecture, because as I said in the intro, the professor hates the textbook for this chapter because it doesn't really explain much. So if you really want to learn more about the subject or try to figure out what's going on, it's best to go look back at the lectures that he did, because those are packed full of information. Now that we got that out of the way, we can continue. So to start off this monster of a problem, this problem is from Berlin, or I forgot how the professor said it, Berlin article. Feel free to refer to it. The goal of the problem is to prove that for an isothermal quasi-static process on an ideal gas, the change in entropy is the change in S is equal to Q over T, where Q is the heat transfer, T is the temperature, and as I wrote to the side right here, isothermal means possessing a constant temperature, and quasi-static means the thermodynamic process happens slowly enough for the system to remain in internal equilibrium. Now those will be useful later on, but for now, just note that this equation right here that he explained in the lecture is the number of microstates that contribute to a macrostate, and that will also be used later. Now, to begin the problem, we have to go with the setup. Now, these are two identical containers, except the warm bricks are used to keep the stuff at a constant temperature, and they're both filled with an ideal gas, which will also be useful, as shown right here. Since we're working with an ideal gas, we can draw on our old knowledge from the previous chapter of PV is equal to nRT, and that will be used later on in the problem. I feel like I'm saying that a lot, but I guess it's okay because it's actually true. And the relevant information for this problem is that E thermal is equal to the work on gas plus Q into gas. Now, if we actually tried to solve that out for this situation, we know because of the description earlier that the internal energy change is 0. So E thermal is 0, and we just have to find the work on the gas and the Q inside. So the work is equal to the negative pressure times the change in volume, and the sign is negative because the volume of the gas is increasing. If the volume of the gas was decreasing, it would be positive. And Q is equal to, actually, that should be positive right there, because I moved the work over to the other side. So it should be Q is equal to P times delta V. Now using that P right there, we can plug in this form of the ideal gas law right here to find that Q is equal to nRT over V times delta V. And you can ignore this part right here since, again, it will be used later. Now that we solved that part out, we can finally go on to step 2, which is explaining why when the volume increases, why this scales with volume to the power of curly n, which is equal to n times Avogadro's number. Now, I put a simple explanation right here to the best of my abilities, but the reason why n, or this curly n, this n right here, is proportional to v to the power of n, is because the microstates are instances of the positions of each atom inside of the volume. So in a small cube, like about the size of my fingers right here, there's not that much different combinations of locations for the atoms or where they can be. But if it was this big and maybe this wide, as opposed to the previous one where it's this small and this small, there's a lot more combinations of where the atoms can go. So The possible microstates grows proportionally with the volume, so the number of microstates for multiple atoms should be the product of what we found for individual atoms. Thus, the n times Na, Ny, it is proportional to the volume. On to the next part, 1.3. This will be a doozy because now we're going into some plug and chug mess. So starting off, it gives us the ratio of n final over n initial. And using that, we can start off with solving out what is n final and what is n initial. As stated in the previous problem, n is equal to v to the power of n. And so n final should be the v plus the increased amount of v to the power of n. And if we actually try to create that in the same form of this ratio right here, it would end up as something like this. V plus delta V over V to the power of n, and it becomes 1 plus delta V over V. If you were reading the problem and you were wondering where this step came in, this is the whole entire reason I'm showing you this diagram of how it would work out. Now, if you logged both sides, it would end up looking somewhat close to the form of log 1 plus x, which the professor suggested that we use for approximation. We know that delta V over V is assumed to be very small, so we're allowed to assume that delta V over V is our x in this approximation method. And so we can say that, well, before that, the curly n at the very top moves to the front using log operations. And then we use the approximation to convert log 1 plus delta V over V to n times delta V over V, which is the x. And just like how we found earlier in this part of the problem, we can actually convert this part so it becomes delta V over V is equal to Q over the divided out nRT, and plug that in right here. And then we can also plug in the curly n is equal to n times regular Na, and cancel out that small n and plug that in. And given in the problem, we're also given R over Na is equal to the Boltzmann constant, which we plug in right here. Now, after all of that, at the very end, using equation 7 and equation 6 and all the steps that we had before, we can finally plug and chug S final minus S initial is equal to Boltzmann constant times log n final minus log n initial, which we know from our previous problem right here. It looks kind of familiar. So we just plug in what we had at the very end of our last part into log nf over ni until we finally get the Boltzmann constants canceling out, and our final answer of Q over T is equal to the change in S that solves the initial problem that it asked in part 1, right here. Sorry it went on a bit longer than I thought, but this is one doozy of a problem, and I hope you have a nice day, you absolute legends.